Hello, welcome to my channel. Today we'll be looking at a law of distance and absorption of gamma or beta rays. And in this experiment, we'll be using the cobalt 60. So we'll be using the cobalt 60. That's the isotope that we'll be using. Cobalt 60. So we'll be using this isotope. That's the elements that we'll be using. This isotope. Now, first of all, this is our Geiger-Muller counter. 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 Now, we need to set this knob to 60 seconds, the timer to 60 seconds. Now we can turn on the alarm. Okay, turn on the alarm system. Now this is the start and stop, and then the reset button, right? Now the first thing that we'll do is we need to measure the background radiation, IBG. So we need to measure IBG, that's the background radiation. We need to check the radiation in the lab first. So that's the IBG, we record IBG. So to do this, we start, and then the counter will be reading. The Geiger-Muller counter will be reading. The Geiger-Muller counter will be reading. So we are still measuring the IBG. That is the background radiation. Now when the counter stops, the alarm will be fast. It will be faster than how it's beating now. And then the values here will no longer be moving. So after that, we know that that's the value of the radiation we have in the room. So we call that the IBG. So currently it has stopped. You see, currently the counter has stopped reading. So the background radiation is supposed to be 33, right? So we can record that one. We can record the background radiation. Then after that, we need to also record the radiation without the absorber, right? Now after doing that, we need to record the radiation coming from the isotope. The radiation coming from the isotope. So we call that one I0. So that one is supposed to be I0. That's supposed to be I0. I0. So to do that, we need to stop this. Now that we have IBG, we need to stop this. Reset. Then we can introduce the isotope, the cobalt 60 isotope. We introduce the cobalt 60 isotope. So we place that one here. Okay, now that this is set, we need to record, as I said, I0. We need to record I0. Now, you can hear that the alarm for the Geiger-Muller counter is beeping fast because of the introduction of the radiation. Because we know that cobalt 60 disintegrates into beta and gamma rays. It disintegrates into beta and gamma rays. So now that we are done with that, we start recording our I naught. So we start this. Then the gauger molar counter also start reading. So we can notice that the radiation in the room I naught, when we recorded that one, was only 33. But as at this one, we are getting about 100 something plus, which shows the intensity of the gamma and then beta rays that this particular cobalt 60 isotope is emitting. Then these radiations are very dangerous to the body. So normally this experiment, when you're done, you need to wash your hands. You don't have to take long or waste so much time in doing it, because your body will absorb all the radiations. So that is the value for I naught. So that is the radiation we get when there is no absorber between the probe and the isotope source. The probe and the isotope, when there is no absorber in between them, this is the radiation we get. Now we can now construct our table, right? We will use different elements. So we have lead. These are lead. This is iron, right? To different thickness. Lead. We have concrete. We have lead. This is lead. This is aluminium, and this is iron, right? Iron, aluminium, lead, concrete, and glass. So to summarize everything up, what we do next is we stop. Now that we have gotten this, we stop this. We stop it. Then we introduce an absorber, right? We introduce an absorber. So we can introduce an absorber. So we use the vernier caliper. We use the vernier caliper to check the thickness of the absorber, right? Yes, so this is 0.5 mm. Then we place the absorber here, right? This way. So we introduce the absorber. We can start with the aluminium, 0.5. Then we'll start this. And then we also read the intensity of the radiation that will pass through the 0.5 mm aluminium. After we get that value, after this stops and we get that value, we change this, introduce the 1 centimeter aluminium absorber here, right? We change it to 1 centimeter. We are increasing it, right? Then we reset, then we start. We reset, then we start. Then we also check the intensity of radiation that passes through the 1 centimeter aluminium, right? So this is 0.5, this is 1 centimeter. So the next thing we do is to increase this. We increase this slabs. We join the 0.5, right, and the 1 together. And then we also check start, reset, and start. Then we check that one too. We record the intensity. So we do from 0.5 to like 3 centimeters. Okay. So that's for the aluminium. When we finish, we use the same procedure for the aluminium to record that one for iron. So iron too, this is the 0.5. This is the 1. This is the 0.5. Then 2 of this will be 2. we add this 2.5, so we check all that. Then we do for lead as well. This is lead. This is lead. Lead is heavier than iron, so this is lead, Pb. This is lead, Pb, right? So we do for this, lead, concrete, and then glass. Then after that, we draw the graph for that. Now, this is the fundamental equation that we'll be using for this experiment. If we are plotting the intensity here, right, that's the activity. The values that we got here, we'll be plotting that one against the thickness, which is D. Now, in doing that, we can say that this U, right, this U in front, this U here is the absorption coefficient. So that is the absorption coefficient, right? This is the absorption coefficient. So it should give us a slope of -1, and then this should be our intercept, right? Because the lines we'll be getting, if we are plotting all the observers on one graph, they will be looking something like this, right? Then, so this against D, and then the slope should be -1, right? This represents the slope, where this is our absorption coefficient, right? So hence we can find the decay constant. We can find the decay constant for the experiment, right? So the half-life for cobalt 60 is 5.27, right? So we can see this is lead, Pb, right? We can see this is aluminium, Al, right? We can draw the table for the other elements, I mean the other absorbers, for concrete, for glass, and then for iron, Fe. Okay, thank you very much.